Hello everyone, my name is James Thorne. Welcome to this talk about our paper outlining the vision of neural databases and how we can overcome some of the key limitations in natural language processing to scale state-of-the-art NLP methods for large-scale data management. Databases with predefined schemas can scale to millions of records and are able to efficiently answer a very wide range of queries, which are specified in a formal language. But there's a trade-off here. While we can scale to large sizes with traditional databases and make queries that are arbitrarily complex, the schema must be defined in advance. This makes it difficult to model the wide range of concepts captured in user-generated content, such as the knowledge one might wish to store and query using a digital personal assistant. This paper investigates whether it's possible to reimagine the reliance of databases on a fixed schema. Successfully doing so would help unlock the vast amounts of knowledge captured in free text. And if we can query over it in natural language, this could allow any user to make use of this data. Our vision is to build a neural database that sits at the intersection of natural language processing and large-scale data management. Unlike traditional relational databases, a neural database does not require a fixed schema or a symbolic representation. Instead, facts are represented as short episodic textual statements that update the state of the world, where new facts are appended to this ordered list. We choose this storage media as it allows us to inspect which facts are used when answering questions, as well as easily update or delete facts by appending or removing items from this list. This allows us to apply methods from NLP to ask questions over these stored facts, again using natural language. Our assumption is that these facts could be inserted in an order where similar topics may not necessarily share locality, and statements that pertain to different events or topics could be stored alongside each other in the same database. Result sets can be generated by reasoning over an appropriate subset of these facts, either by extracting information, such as listing the people who live in the USA, or performing some sort of computation, such as counting, returning this as an item to the end user. A class of models commonly used in question answering in NLP is an encoder-decoder model. For neural databases, we can exploit the same architecture, concatenating all facts in the database, as well as the query, into some sort of latent representation, and train the model to predict the most likely sequence of tokens that represents the answer. We perform our initial experiments with a transformer model. This is a very high-capacity feed-forward neural network, which contains repeated layers that contain an attention mechanism and is representative of the state-of-the-art for NLP today. The introduction of attention has benefited many natural language understanding tasks, allowing long-distance dependencies between tokens to be captured and scored. This is because each token is conditionally encoded in the context of others. This can be exploited in neural databases to consider many-way joins, where the encoder jointly encodes all supporting information between multiple facts in the query. Additionally, tokens can be disambiguated in context based on other tokens and the query. While the use of attention has led to significant advances, it comes at a cost as, without modification, the attention mechanism considers all pairwise interactions in the input, which has quadratic complexity, and limits the number of tokens that can be encoded. We evaluate our models and consider their ability to process simple queries on synthetic databases. For this model, we use a T5 transformer and train it with tuples containing databases, questions, and answers, all synthesized from Wikidata. Because of the quadratic complexity of self-attention, we limit the size of databases to be less than 50 facts, as extending beyond 1024 tokens typically requires architectural or engineering changes to overcome GPU memory limitations. Our evaluation considers a number of query types that would be considered a core part of a database management system. For example, selecting facts, or joining multiple facts together for a query, or performing simple numerical reasoning tasks, such as counting or aggregating the results. These models are evaluated with different sets of facts from the database too. We consider perfect IR, which considers only the relevant facts being input to the model, as well as whole DB, where all facts from the database are input. As, to scale for larger databases, we'd have to consider the combination of a retrieval as well as a reasoning system. We also consider DPR and TF-IDF. Preliminary experiments indicate that while the model can process simple query types on small databases, there are still several avenues where improvements need to be made. This is especially pertinent on the right-hand side of this graph, where numerical reasoning is required. For example, for the count query type, model accuracy is low, and furthermore, requiring the model to consider all facts in the database further reduces answer accuracy. For answers requiring numerical reasoning, the transformer is predicting a sequence of tokens which is a string representation of this numeric answer. There are no mathematical guarantees, and related work has indicated some question over how neural models generalize in this setting. So we're evaluating on small databases of less than 50 facts, and to scale this type of query processor to larger databases, we'd have to incorporate retrieval. Retrieval errors from DPR and TF-IDF propagated for a number of query types, including joins, set answers, and numerical reasoning. These retrievers only operate over a single step and cannot incorporate additional information required to complete the joins. Furthermore, for the min-max query type, the lack of matching tokens between the query and the facts resulted in near-zero recall for TF-IDF. An example of this would be asking a query such as who is the oldest, and having only facts in the database that described when people's date of births are, for example. We need to ensure that the retriever is able to perform multiple retrieval hops, incrementally adding information relevant to the query and based off the currently selected facts. The two baseline methods we've explored don't do this and can saturate the model with irrelevant information. One way we can scale to large databases is to exploit the structure and how facts are stored and consider local operations over smaller sets of facts, rather than one global operation that operates over every fact. We achieve this through two architectural choices which consider independent operations over sets of supporting facts. The support sets can be reasoned over independently in a parallelizable, non-blocking manner, with models that form part of a larger result set. When generating this result set, we can compose the outputs using conventional computation, for example, counting, argmin, or argmax. We propose an architecture that has three components: a support set generator, an operator that performs selection, projection, and joining of facts called NeuralSPJ, and an aggregator at the end of this pipeline. At the core of the neural database architecture is this encoder-decoder model we've encountered earlier. The NeuralSPJ is performing simple query processing with functions we've demonstrated that the model has capability for, and is not performing numerical reasoning. This allows the model to do what it does best, providing it with an appropriate support set and using it to generate a limited derivation dependent on the query. This derivation is then aggregated by the downstream aggregation function. In this example, where we have three facts, our query asks how many people's spouses are doctors. The support set generator generates a partition of these facts, yielding two support sets that are independently processed by two NeuralSPJ models. The top support set is filtered by the SPJ, whereas the bottom one outputs a string literal John. The set of all string literals is counted by the aggregator, yielding the output 1. At the core of this model, the NeuralSPJ is performing query-focused information extraction from the facts. In contrast to the baseline system we demonstrated earlier, which was trained to generate complete answers, the NeuralSPJ only needs to be trained to filter irrelevant information and extract a string literal used by the downstream aggregation operator. This further gives a mechanism to explore how different facts and representations of information in the database are projected to form a part of a larger answer, meaning that shortcomings in language understanding by the SPJ can be identified and remedied. This also aids our training data generation too, as we don't need to ensure global completeness when generating the question-answer pairs. We just need to consider a local mapping from support set to its intermediate derivation. With our architecture, our results indicate that we are able to overcome the challenges of scale, as well as combining retrieval and reasoning. In direct comparison to systems made of contemporary NLP methods, our results indicate that if we had a perfect support set generator, we could scale the NeuralSPJ and aggregation to databases of arbitrary size. The weakest part of this model was the introduction of the support set generator. Multi-hop reasoning remains an open research direction in NLP, and our database not only requires multi-hop reasoning, it requires it over multiple sets. However, the answer accuracy is more stable over a range of database sizes than models based on previous work using TF-IDF and DPR. These baseline systems had no notion of submodularity, returning the most similar facts to the question, regardless of whether similar information had been returned or not. Continuing our research in this direction, there are 4 areas for further development which we would want to explore. The first is to consider a deeper understanding of semantics. In our baseline, we made use of a unique names assumption for entities, where one mention corresponds to one unique entity. However, in the real world, the mapping between aliases and entities is bijective, and we must appropriately ground entity mentions. Additionally, some updates, such as getting a new job, would update the state of the world, meaning that previous facts no longer hold. We would further want to explore training data efficiency, and see how little data is needed to apply neural databases to new domains. However, if we do this, we'd want to ensure that biases the model captures do not perpetuate negative societal biases. And finally, the neural components we generate have been explored in isolation, but there are vast arrays of unstructured content that are, such as text and images, locked away in databases. How can we build hybrid architectures that exploit the best of both worlds? To help further research in this direction, all code and data is available, and if you're interested in the technical aspects of this paper, please check out our paper, Database Reasoning over Text, that further explores neural databases from an experimental setting. Thank you for your attention. I look forward to receiving your questions.